Well, welcome to our continuing study of chemistry. We're going to focus on the periodic table. And if you take a look at this view of the Webb elements periodic table, you will notice that it has an unusual shape. If I were going to organize something, I would not necessarily have a weird shaped box to define the area where this goes. And there's a reason for that, and that's part of what we're going to learn during this chapter, this unit. You will notice that the number 1 is followed by the number 2. I don't know why they're so far apart. And then 3, 4, 5, 6, 7. And that pattern continues all the way along until you get down here, and then you go from a jump from 56 to 71. Well, where'd those guys go? Oh, they're down here. And so we'll learn why these are in different areas and why it is arranged the way that it is. So there are your usual vocabulary words that you will learn while you're in here, but we're going to start out just looking by a major division of the major division on the periodic table, and that's between the metals and the nonmetals. The metals tend to be, and I'll just give you some of their properties, they tend to be shiny. And that sounds like a very easy word, so chemists make it a little more difficult. They use the word luster to define the shininess of metals. Metals are good conductors of heat and electricity. And they are ductile and malleable. Those words might be a little bit unusual for you, so ductile simply means that it can be drawn into a wire. So a nice thin long piece of metal would be called a wire. Malleable means that it can be pounded into a sheet or different shapes. So it gives you a little idea. So a nonmetal is going to typically be dull, non-conductive, and rather than malleable or ductile, we will define it as brittle. So a lot of the nonmetals you will notice will have or can exist in a powder form, where most metals are not going to exist in that way. And if they do, they have very different properties than your nonmetals. So on the periodic table, we have rows going across that are important, and they're labeled typically as 1, 2, 3, 4, 5, and we'll learn what those are. But that is called the period. So the periodic table is called the periodic table because there's a trend that happens as you go from left to right within a period. And then as you go up and down a column, there's other trends that we see. The columns are called either families or groups. And what is very important about those family or groups is that they share, and this is going to be major for a chemist, they share chemical properties. They tend to react the same way as other elements within that column. So as we look at the periodic table, the importance of the periodic table comes down to the sharing of chemical properties and understanding what happens as you go from left to right across a period. Now I've drawn in a little bit of a heavy line here, and I'm just going to retrace it because this defines the separation between our non-metals, which are over here on the right-hand side, and then the rest of the periodic table is going to contain all the metals. So if you were to look at the periodic table, you would say that elements on the periodic table are primarily metals, and that would include going this way and all the way up to there, all the way over to here. So you'll notice something like aluminum is a metal, and that's the place where aluminum belongs. The dividing line that I've drawn here, just above aluminum, these are called the metalloids. And the metalloids and you'll see this word on the next page. The metalloids are the dividing line between your metals and your nonmetals. So nonmetals, which are brittle, dull, and metals, which are shiny and conductive and ductile and malleable, metalloids seem to have properties either of one or the other, but it's unpredictable. You have to look at each one individually to know what its properties are. So let's go and delve a little bit further into the periodic table. So just a little information about what we have. Elements in the human body. We are made up of 65% oxygen. And I know most of you know that the formula for water is H2O, and it looks like there'd be twice as much hydrogen as there is oxygen in the human body. But hydrogen is only 10%. Well, this is a mass percent, and the mass percent means that oxygen, being 16 times heavier than hydrogen, is going to have a larger mass percent than hydrogen does overall. But yes, our body is mostly water. And then these elements in the human body are a little bit different from the distribution in the Earth's crusts, oceans, and atmosphere. So oxygen is still a major element in our Earth and the oceans and atmosphere around us, and at about 50%. But then number 2 on the list is silicon. So as living beings, carbon is the molecule of life. That's the basis for organic chemistry. But for minerals and such, silicon tends to be more important, and so that's why you're going to see a larger percent there. So just a little information about where these elements are in the world in which we live. So what we're going to do is we're going to label the periodic table below with the designations that are here. And these are families or groups within the periodic table. And so just to reemphasize it, because this is very important, is that these family or groups tend to react the same chemically. And that is their importance to us. So let's go ahead and label these. And let's start with the far left-hand side. This first column here, these are going to be called the alkali metals. So the first column, sorry for that little misspelling there, are the alkali metals. And then right next to them in that second column, we have the alkaline earth metals. And that might help you to remember something, is that column 1 only has one word, alkali metals. Alkaline earth metals you'll find in column 2. And then, as we look again at our list of words that we're putting in here, alkali metals, alkaline earth metals, and then halogens. So we're going to go to the other side of the periodic table, and this group right here, they are called the halogens. So the halogens are going to contain things like fluorine, chlorine, bromine, and iodine. Next to that, we have the noble gases. And the noble gases will include helium, and then neon, argon, etc., down the list there. Those are the noble gases. We call them noble because they don't react with anything else. They tend to be standoffish, like nobility back in the old days. They would not mix with the common elements. Heaven forbid, they're too good for that. So these are the noble gases that are up there. So going down our list, we have the transition metals, which take up a huge chunk of the periodic table. So if I could define it in this way, I'm going to put a box around the transition metals here. And the transition metals comprise this large portion of metals in there. So all of those would be included. And then we might want to make special note of a couple of metals that are over here that are called the post-transition metals, and they typically act like the transition metals. So lead and tin are over here, and they are the transition metals. So let's look at our metalloids. So our metalloids tend to be in this area right here. And some people include these as metalloids, these two down here, but we don't need to worry about that. That is not going to be important. So far we have looked at alkali metals, alkaline earth metals, halogens, noble gases, and then finally the transition metals here in the middle. These are all families, and they tend to react the same chemically. But we also have these two groups down here. And this column labeled 6 is labeled that way because it continues from what this element is. And this is lanthanum, this is actinium right below it. So the lanthanides follow numerically from lanthanum, and then this group here, these are going to be, of course, the actinides. So you will want to know all these groups and how to find them on the periodic table. And pause. So we're going to look into how the elements were first discovered, a little bit of their development here. The Greeks thought they had the world figured out back a long, long time ago, and they knew that there were 4 elements. Now, when you say the word know, obviously, they thought they knew that the earth was made up of earth. So everything that was kind of around them was earth, wind, fire, and water. And they thought that if there's anything that exists, this is how you could define it. It's either going to be of the nature of earth, wind, fire, or water. The Greeks also termed the word atom about 2000 BC. Now, they didn't have any idea what atom meant at that time, and so it was more just thinking about what an atom is. So for 2,000 years, the Greek concept stood. You may have heard about in the Middle Ages, there was something about alchemists, people who thought that they could make gold out of cheap metals. And they were probably your earliest chemist, although many of them were not very good scientists in terms of following a methodical way to do things and trying to discover properly what is possible or not possible. So it wasn't until the early 1800s that John Dalton proposed the following theory regarding atoms. And I am going to pause in between in order to write in the information, and you can pause this video as well to help you. So John Dalton became convinced that elements were made of tiny particles called atoms, and he was using some very fundamental tools in doing this, but he knew that that was the... Dalton also said that all atoms of a given element are identical. This is the only one of the 5 ideas in his atomic theory that needs to be slightly modified. He did not know about isotopes. Isotopes have different numbers of neutrons, but the same number of protons as an element. So isotopes was something he didn't know about, but that is the only one of these 5 that he needs to. He also said that atoms of one element are distinctly different than atoms of another element. As you can imagine, this would have made the alchemists very angry, because now their livelihood was being put into question. If all atoms of a given element are identical, and atoms of one element are different than atoms of another element, then there's no way that you can take lead and make gold out of it. Now, we can do that today using a nuclear reaction, but that's not what they were looking at that time. So part of the mystery of matter was, where did all the materials in the world come from? So the fourth part of John Dalton's atomic theory is that atoms of different elements combine to form compounds. In this fourth postulate there is two laws. One of them is called the law of multiple proportions, saying that whole units, i.e. atoms, actually come together to form compounds. And if you have two elements that combine, they will only combine in whole atom quantities. It's not important that you remember that, but that is the law of multiple proportions. And then he also had the law of constant composition. This is one that's going to be important for you to remember. So, law of constant composition basically says that regardless of where you find water in the world, it's always made up of two atoms of hydrogen and one atom of oxygen. If you were to look at salt, salt is always made up of one atom of sodium combined with one atom of chlorine. So when we look at compounds, they have constant composition. So if we have polluted water, then you have water plus something else. So the ocean has salt water. That's a combination of water and salt mixed together. So the last one involves the law of conservation of mass. And Dalton said atoms are not created or destroyed in chemical reactions. They are simply rearranged. So that is Dalton's theory, and you have to understand that at that time this is an incredible amount of information that he has put together with some very, very basic tools back in the 1800s. So now we're going to take just some of these ideas and show practically how they work out. We can write a compound as a name, such as salt or sodium chloride, but we can also write that name as a formula. And so we call that a chemical formula, and it's just an abbreviated way of showing what something is made up of. It shows the types of atoms and it shows the number of atoms. So an example would be sodium chloride. NaCl is the chemical formula. Water is H2O. And as we said before, this involves one sodium and one chlorine for salt. And this is two hydrogens and one oxygen. So you'll notice that the subscript defines what comes before it, not what comes after. And as you look at chemical formulas, that will be important to remember. So let's get some rules for writing formulas down before we continue. First of all, each element is represented by its symbol. That's why we wrote down H2O. There's hydrogen and there's oxygen in water. There's sodium and chlorine in salt. The number of atoms is shown to the right and as a subscript of its symbol. And then finally, if there's only one atom of an element, then we do not use a subscript. So in the example above, H2O and NaCl, there are two hydrogens and one oxygen. The oxygen does not have a 1 after it. NaCl just says NaCl. There's no subscript 1 that's shown after that. So when there is only one, we don't do anything. All right, so what I want you to do is to just simply show me how many atoms of everything there is in each of these compounds. So my two examples, H2O and then NH3, which is also known as ammonia, and you'll find ammonia in window cleaner, has 1 nitrogen and 3 hydrogens. So go ahead and do the remainder on this page, and we'll start section 3.5 on our next video. So video 1 is ending here for chapter 3, and then we'll begin here for the second part of the chapter.